Welcome. Let's take a look at number 4. So it says a fair number cube with faces labeled 1 to 6 is rolled. So just another name here for rolling a die. And we'll take a look at a regular 6-sided die. So our sample space, we could land on, have it roll a 1, 2, 3, 4, 5, or 6. And we'll take a look at the probability of rolling a 4. So what I've done is just written the sample space across the page here, so we can go ahead and circle events of interest. So the chances that I roll a 4, so of course out of those 6, just one of those ways results in 4, so 1 out of 6. And then my chances of not rolling a 4, so that would be either 1, 2, 3, 5, or 6. So the other 5 numbers out of those 6 that are not a 4. All right, and probability of rolling at least a 4. So at least 4 means 4 or more. So 3 values out of the 6. And we're just staying in fraction here, and you don't need to reduce. And then let's return to our idea of union. So union is when we see or in probability. So probability of getting a number greater than 2, or it's odd. So or means combine the sets and then count those outcomes. So we'll take every number greater than 2. I'll circle those. So greater than 2 would be 3, 4, 5, 6, along with any number that's odd needs to be counted as well. So we need to circle the 1, and we've already circled the other odd numbers here. So all the numbers that are either greater than 2 or odd would be 1, 3, 4, 5, or 6. So 1, 2, 3, 4, 5. So 5 outcomes are either greater than 2 or odd. Some of them happen to be both, but those get counted as well with or. All right, and I'm going to go to that same question below here, but with intersection, so that'll be our word and. So probability that a roll is greater than 2 and it's odd. So and means only count outcomes that are common to both sets. So it has to meet both conditions. So in this case, I'm going to just list the numbers greater than 2 here. So greater than 2 was 3, 4, 5, or 6. And then the second condition, odd numbers, I'm just going to list all the odd numbers. And then we want to know the probability that it meets both of those conditions. So any numbers that they have in common. So 3 meets both conditions. 5 meets both conditions. So 3 and 5 are both numbers that are greater than 2, and they are also odd numbers. So 2 out of the 5. I'm sorry, 2 out of 6, 2 out of the 6 outcomes. Okay, and then I'm going to come over here to my E. So let's get the probability a number is greater than 4 or less than 3. So or is combine the sets. So every number greater than 4 gets counted. So that would be 5, 6, along with any number less than 3 gets counted, and numbers less than 3 would be the 2 and the 1. So 4 out of those 6 outcomes meet one condition or the other condition. And then below it, we'll do our and. So greater than 4 and less than 3. So numbers that meet both conditions. So here I am going to list the numbers greater than 4. So that was 5, 6. And the numbers less than 3 were 1 and 2. And the numbers common to both sets, well, in this case, there are no numbers in common, so the probability would be 0 out of 6 or 0. So there are no numbers that meet the condition of being greater than 4 and also being less than 3. All right, so that's just a little review there of union and intersection. And then let's go to what we call the law of large numbers, which is going to bridge our 2 types of probabilities together, the experimental and the theoretical. So the law of large numbers states that the larger the number of trials of a probability experiment, like spinning a spinner, the greater the likelihood that the experimental probability will be close to the theoretical probability. So let's take a look at this. So number one, so we have a dial with 6 equally sized slices. 2 are blue, 1 is red, and 3 are yellow. The dial is spun and stops on a slice at random. We spin the dial 10 times and our results are shown to the right. So to the right is our experiment. So we actually conducted an experiment. So we're going to talk about experimental probability, but before we do that, we're going to talk about theoretical probability. So theoretical probability does not involve looking at the experiment, it involves looking at the actual spinner itself. So I'm going to write the formula here of getting yellow. So I want to know the theoretical probability of landing on yellow. So it's going to be the number of yellow slices over the number of outcomes in our sample space. So on the spinner itself, the sample space is the set of all possible outcomes. So in this case, the number of items in our sample space, there are 6 slices. So we have 6 possibilities. So the probability in theory of landing on yellow, there are 3 yellow slices out of 6 possible slices. So in theory, that will be 0.5 or 50%. So half of that spinner, 50% of it, is comprised of yellow slices. So that's what we expect in theory to happen, but that won't match necessarily what happens on the experiment. What the law of large numbers says is the more times you conduct your experiment, the more likely it is that you're going to see that theoretical probability appear. So let's take a look at what we did here with our experiment. So the number of spins that we had, 2 landed red, 8 yellow, and 0 blue. So that number of spins is representing the frequency of each of the outcomes, F. And in total there, if you add the total, that would be 2 plus 8, 10 spins. So we had 10 spins of our spinner, and these were the resulting frequencies. So based on the experiment, the probability of yellow, so frequency over n, in our experiment, we got yellow 8 times out of our 10 spins. So that would be 0.8 or 80%. So what happened in our experiment is pretty far from what we said should happen in theory. So when we do an experiment a small number of times, so they're called trials. So in this case, we only spun it 10 times. So that experimental probability might be pretty far off from theory. What the law of large numbers says is that the more times you spin the spinner, the more likely it is that this value for your experimental will be close to what actually is in theory. So instead of spinning it 10 times, if I spun this spinner 1,000 times, I'd probably see our experiment getting close to yellow 50% of the time. So the more times we do the experiment, the more likely it is that experiments match theory. Okay, so let's try this one, number 2. The state lottery is examining the machine that randomly picks the lottery numbers, and on each trial they experiment, the machine outputs a ball with one of the digits 0 through 9. So every ball has a digit on it, and the lottery board was testing the machine for 200 trials, and these were the results. All right, so let's just first make a note here that the possible outcomes, these are your sample space outcomes. So these are the digits that could be chosen by the machine. So the number of items in the sample space, so the digits here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 possible digits. And when we did the experiment, the number of trials, so the frequency of each of the digits is shown. If we add up all of the frequencies, that will give us the number of trials, n. And if you add those up, you will get 200. They do tell me they did 200 trials. All right, so for this one, let's start with experimental. So we'd like to do the experimental probability of getting an even digit. So when they tested the machine, we're going to look at the results of their experiment. So frequency over n. So we want to look at all of the times they got an even digit. So the even digits, 0 is an even number. I'm just going to put even here. 0 is even. Of course, 2 is even. 4 is even. 6 is even. 8 is even. So they got 0 12 times. The digit 2 came up 20 times. The digit 4, 24 times. The digit 6 came up 18 times. The digit 8 came up 15 times. So the number of times they got an even digit, I'm just going to add up all those frequencies together for all of our evens. And that's going to be out of the 200 trials. So I'll do that over here on the calculator, 12 plus 20 plus 24 plus 18 plus 15. So that machine put out an even digit, 89 out of the 200 trials. And I'm going to go ahead and put that in decimal, 89 over 200, 0.445, 0.445. And I'm actually going to write that as a percent as well. So the machine turned out even digits 44.5% of the time. All right. Now, assuming that the machine is fair, so that would mean that every digit is equally likely. Well, half the digits are even digits and the other half are odd digits. So in theory, I would expect to get an even digit half the time. We'll write the formula here for theoretical probability. It's the number of even digits over the number of digits in the sample space. So there are 5 even digits. So if you think of these, I think of them like ping pong balls in a lottery machine that's spitting out ping pong balls. There are 10 ping pong balls. 5 of them have even digits on them. So in theory, I would expect 5 out of 10 times for that machine to give an even digit. So that's going to be 0.5 or 50% of the time. So if the machine is fair, that's what in theory should hold. This is what we got when we conducted our experiment with 200 trials. And so the follow-up question is, assuming that the machine is fair, the larger the number of trials, the larger the likelihood. So this is law of large numbers. The larger the number of trials, the larger the likelihood that the experimental probability will be close to the theoretical probability. All right, so those are 2 examples for you, kind of bridging the relationship between the theoretical and the experimental.